Okay, so I hope I can. I had to rewrite now my complete talk because I was on short notice given the opportunity to give this colloquium on Monday, and I tried to be as different as possible as I can. To start off, here's my let's say scientist introduction to the Galactic Center. You have to observe in the infrared, and you have to zoom to a high degree in order to see the relevant scales. You can see here, if you zoom into the optical, you essentially run into the dust screen, the extinction, and you have to go to infrared wavelengths, which we are doing now. And then you can see in the middle coming up at this red cluster, which is the nuclear cluster where the black hole is located. And zooming on further and further, at some point you will notice that that image is not sharp anymore. You can see that it's slightly blurred, and that's the moment when you actually hit the atmospheric limit, so you need adaptive optics to overcome that. Turning on adaptive optics, you actually can zoom into the central arc second, and here come 16 frames from the central arc second, which we've recorded in that particular case from 92 to 2008, showing the motion of these objects there. In particular, you see the brightest is one of the brightest stars going in a nice ellipse. The model, so we have on the order of 40 stars here. The model which you need to describe the orbits for these 40 stars, it's extremely simple. It's essentially one parametric. It's the mass of the black hole what you need, and that mass comes out to be 4 million times the mass of the sun. So the cartoon version of that stellar system here is that we have just seen these S stars, how we call them. They are young, and they are on. We can see that they are on orbits. A bit further out, there's a disk of even younger stars. They are only 10 to the 7 years old or so. The disk is well defined. Of course, all this is embedded in a sea of old stars, and there might be stellar black holes and neutron stars, white dwarfs, and so on. And I think we have to add another specimen to this picture, namely that there might also be lumps of gas flying around. So for those of you who are tired already at that point, here's the summary of my talk. I think no observation requires the presence of a star inside of G2, but naturally it's very hard to actually exclude a star inside. And in the following, I've decided that I would like to collect the observational facts. What do we know about G2? So I think the first point to make is that we know that G2 is on a highly elliptical orbit, which passed pericenter in 2014, and that orbit coincides with the stellar disk, which I've just shown to you. You can see here the orbit again. It's well defined in the sense that you measure an acceleration. You do see a change in radial velocity. You actually see a change of the changing rate in the acceleration. So there's more than 6 dynamical quantities defined, so that orbit is very well defined. The initial estimate for the orbit, actually, if you might remember, was that pericenter passage would be in summer 2013, and I think rightly so. Our colleagues from UCLA have corrected that to a date later, because they showed that the L-band astrometry we were using was biased, and one should actually use the gas measurements to determine the astrometry. So I think that is undoubted. The next point is that G2 is visible in recombination lines in bracket gamma, helium-1, and Paschen alpha. For those of you who are observers, Paschen alpha is a bit of a surprise because that's usually between the H and the K band. Yet here's a spectrum of G2. You might not easily read it. Here's the bracket gamma line. This is the helium line. And this very bright line here, this is actually the Paschen alpha line. Usually you're not able to see that from the ground. However, the atmosphere is varying so quickly in its transmission function that due to the high redshift of G2, actually the line happens to fall in the window that you can see it, and you can see that makes actually most of the signal to noise. And if you remember now to do these position velocity diagrams, you can actually do them in all lines. You can just apply, and you can see, of course, a consistent picture that the position velocity diagrams are all the same. So from this gas, we essentially can infer that a mass of or the density of the cloud. We know that the object is optically thin. It's plausibly fully ionized simply by comparing with the UV radiation field of the surrounding stars. And then you can calculate that it should have around 3 Earth masses, 3 meaning a number between 1 and 10 or so. Bracket gamma luminosity and K-speed recombination theory is what you need for that. The luminosity is on the order of 2 times 10 to minus 3 solar luminosities, and the density comes out to 10 to 5. The energy available is actually 10 to 48 erg, so that's the energy if you dump G2 onto the black hole. And the mass of G2 is actually larger than the mass in the accretion flow if you restrict the accretion flow to the pericenter distance of G2. So moving on. the gas is tidally evolving like an ensemble of test particles. You remember these position velocity diagrams where you sort of look for that line, and then you can create this 9-frame movie here where you can see beautifully how the gas is getting stretched and then swinging over onto the other side. The movie doesn't continue yet, but of course we have applied for observing time in 2016 to do that. That is very well described by the motion of test particles, and I think this is actually not a surprise, even if you do a hydro simulation, because if you set up an atmosphere and run the simulation, you can see that this disruption is mainly tidal until the moment of pericenter passage, and only then the hydro effects are kicking in. So that is not a big surprise that we do see mainly a tidal evolution, and you see that the hydro effects are very weak, and they only get strong after pericenter, maybe 2 or 3 years after pericenter. So I think that is also not much of a surprise. What is a surprise maybe is what I will have to show in the following. So on that point, actually, I think our colleagues at UCLA agree. I think in their best data set from 2006, they claim that also for them G2 exhibits marginal spatial extent. That is consistent. That's actually the first resolved measurement of G2, I would think, the 2006 OSIRIS data set. However, that statement here is actually disputed by a paper by Valencia Schneider, so the statement here in the abstract of that paper is that they don't detect any significant extension of G2. Well, you have to look at the figure 9 here. You can see here the bracket gamma emission, and they have divided that bracket gamma into the blue and the red half, and what you can see is maybe most nicely here that the red half and the blue half are at slightly different positions. They are not at the same position, and that is of course exactly what is a velocity gradient. If the blue emission is at a different position than the red emission. So I think the velocity gradient is right there. Also, that data from 2014 has become public in the meantime, so I went ahead and downloaded their data, and we have reduced the data doing position velocity diagrams. So you can see here, essentially the same structure shows up as in our position velocity diagram. So there's the claim that there was a compact object here and a compact object here. I think this is not sustained by this data set, and the difference is simply let's say how well you analyze, how well you massage the data to show that. Of course, if you take the brightest peak, you might end up taking something here and then later something here, but that is only a tip of the iceberg effect. So I think that statement is safe, that we see gas tidally evolving like an ensemble of test particles. The L-band emission, on the other hand, is compact, but the extent might be compatible with gas. And here's the point which I think is most puzzling. We have here two views of the same object in 2014. On the left, it's the VLT view showing the gas emission. You can see the red shifted and the blue shifted part of the cloud, and they are really spatially separated by quite a bit. And at the same time, more or less, an image was taken with the Keck telescope looking at the dust emission here at 3.8 micrometer, and after subtracting off all the known sources, you end up with a rather compact object here, and I'm sure Gunther will later on refer to that measurement because it's his paper. So here for me is a big question mark. How can that be? And I have 2 points to make in order to explain that. The first point is sort of a word of caution for the left side. The second argument is a word of caution for the right side. The 2014 Symphony data are shown here again. So the red emission corresponds to that side, the blue emission corresponds to that here. And if you actually look at how a test particle simulation looks like, this is sort of a fit where we've tried to model it. It's not a real fit, but we have tried to model it with a test particle simulation. And what you actually see is that that you see a pronounced red and blue side, but actually the point of highest density is actually very hard to observe spectroscopically. And that is because you spread out the flux over so many spectral channels at that position. So if you think in terms of surface density in this PV diagram, the surface density of gas here is actually rather lower than here and here. So we have a decreased sensitivity actually to see that. And so that is issue one. The brightest point in image space is actually faint in the spectroscopy. So there is a bias towards that. Discussing yesterday with Elad, who is sitting there, I actually learned there might be a different reason for that, and I encourage you to discuss with him why there's even a theoretical argument why actually you might see less of the gas emission at that point. The
I had a question. So if you add up all the channels around zero, can you get a significant signal that way?
Well, that's what we've tried, of course. But once essentially you hit the background limit, you don't gain it. It's and this is a simulation, right? And the data you can see how noisy that is. I mean, that hardly stands out. And I agree that one should be able to do it, but yeah, if you're in the noise, you never recover a signal. There's always a limit to it. And these integrations, it's not that we are sort of trying to save integration time. These integrations are 20 hours on source, so that is rather expensive in terms of telescope time already. So I think this is issue one. The second issue is that I'm not so sure what actually that reported L-band source from Gunther's paper is, because if you plot their positions on top of where it is, it actually does not fall right where it should be. It actually falls a bit south of the orbit and south of Sag A star. It matches better the position of Sag A star, I would say, than it would match the position of any of the orbits. You can see here's this data point. It's rather a bit far away, and I think Gunther phrased it carefully in his paper to say that it's compatible. I think you can make that statement. Yet the issue here is that I'm not sure what actually that source is, and in order to retrieve that image, one needed to subtract of sources, in particular needed to subtract of Sag A star, and for that you needed to assume a spectral index, a color of Sag A star, because Sag A star itself is a variable source, so you have to measure it instantaneously from another band and then extrapolate with a given spectral index. So I'm not sure how well one, what actually that source is showing. Not from 2014. The reason is that our imager was taken down in 2014. The observatory, of course, has higher priorities than science, so you sometimes get these effects that your instrument is taken down. So we do have one from 2015 that is upcoming in a paper which a student, Philipp Pleva of mine, is working on. So essentially it's the same game. You have an L-band image, you have a K-band image, you try to subtract of the sources, and then there remains some emission which you try to associate with G2. But this work is still ongoing. In particular, we are not able to make a statement yet whether that object is extended and how well we can trust the position. The interesting accuracy of position is sort of, you need to measure the position of such a blob below a pixel or so, and that is actually very difficult in this in that regime. But I'm sure we will make some statement. We are simply not yet sure what the statement will be. So I think that statement is also given with that. The next point is that there's no photospheric emission is detected of the object. We don't see any light coming from a photosphere of a star. Here is the VLT version of that, and our colleagues at UCLA have essentially done the same picture using different color scales, yet there's a clear detection of G2 in L-band, and it's not there in K-band, and the limit given by Pfeiffer et al. In 2013 is, I think, the best limit so far. It's larger, so the magnitude has to be larger than 20, fainter than 20th magnitude. So what you essentially learn from that is the temperature of 600 Kelvin. That also has been disputed by a paper from Andreas Eckert, where essentially he tries to find an object, and he found a data set in the world where he can find such a K-band emission, and here's the corresponding SED plot. But the argument is twisted, actually. So personally, I don't believe that K-band detection which he's using, and I think Gunther would agree with that statement, that is probably not a real detection. that is an over-deconvolution of the image. But even if it were true, we wouldn't really care, because the observation of of the K-band does not require the presence of a star yet. The detection simply is compatible with a 500 to 600 Kelvin dust, and you can always make a star, of course, faint and hot enough that you cannot see it. What would be a decisive measurement would be if we would be having a point here in H-band. That would be a decisive measurement if we would, at shorter wavelengths, see emission. So essentially, the data set does not require the presence of a star here. You don't need photospheric emission. Simple dust emission with a somewhat higher temperature is completely sufficient. Next point is that there's a tail following G2. You can see here in our position velocity diagrams of the later years nicely how that looks like. We see that tail also in image space, how it's spread out. It's rather faint. And a new data set which is that we have collected is that we have not only now exposed on the central field, but we have spent some exposure here to the left. So that is sort of it feels a bit weird. You look at the galactic center and you take a very precious telescope and you exactly look next to the black hole. That doesn't not feel quite right. Doing so, we have extracted essentially a position velocity diagram along that path which is marked here. That path is interesting because that is where there is an overdensity of bracket gamma emission which is at different velocities. And that PV diagram that is also sort of in constant work. So the PV diagrams you had seen before, they essentially stopped here and was only the right side of that. So here's the position axis, this is the velocity axis. You see the blue side of G2, you see a bit still on the red side, you see here that tail. And then you can speculate where it goes, that tail. So it essentially, you can see it continues. It might smoothly connect to the wind of the star IR16 southwest, but you might also be tempted to see that it simply connects back to the ambient gas, which is here at rest wavelength for bracket gamma. There's also a dust streak which goes along that direction. I think Gunther will tell more about that. So there's a tail following. G1 is that object which is on a similar orbit. You can see it both in gas and in dust. The orbits are similar, although not the same. And the way to connect them, a way to connect them actually is to invoke a drag force model. So far, we have not seen.
How complex is G1 after?
It's actually fluffy. I think it's significant that this is extended here. I've never measured it from that picture myself. In that year, I think the KEC data are a bit better than the VLT data, but I'm not sure. So we haven't seen any increased emission, and I think there have been two reasons to believe that there might be increased emission. One is that the G2 cloud would form a shock in such a star's atmosphere that would lead to X-ray emission, as we have predicted, or Alexander Sadowski has, of course, predicted the radio emission. But the details on that depend on the clumping, the densities, and so on. And I'm not so sure if you have a streamer of gas, how that idea would still lead to a shock. I don't think so. And the other is, of course, the other idea is that you have accretion on such a star. Yet, of course, the center distance of 2,000 Schwarzschild radii is so far out that essentially you still need a viscous timescale to spiral down, and that is unknown. And I think in that paper, Monica essentially calculated it can be up to 100 years or so. So what I would like to point out is that the absence of emission is no argument for the cloud versus star discussion. That I think is sort of also a twist which you need to be aware of. Of course, a star does not create accretion, but also a gas cloud not necessarily accretes that easily. Surprisingly is the compactness in 2008, so that we have actually discovered the object as a rather compact thing, because if you started at apocenter, it should have been already a very long streak of gas when we detect it. However, there are scenarios that work. You essentially have to kick it off with a significant velocity towards the black hole, which is of course consistent with the high eccentricity of the orbit. But of course, one should also say that the stellar scenario also naturally is more compact than that. And the bracket gamma luminosity actually only moderately increased during time. So you can see here what theorists have calculated, that essentially the luminosity should go up in a wind scenario. I think if you take other scenarios where you only dilute the cloud, the emission goes down, but it has been Luckily rather constant for us, because if it would have fainted by a factor 10, no way that we would observe it still. So here's the full list of observational facts. And what does it mean? And I don't want to jump onto the same model again as I did in my talk on Monday, but I rather would like to point out the nice idea which James has provided to us. And I think that idea is also very well still possible. And I mean, that is a collisional debris of a grazing disruption. So you have a red giant star which sort of almost enters the tidal radius. So you rip off a bit of the atmosphere, and then that essentially is G2. And here's simulations of that, how that would look like. You get naturally such a tail and so on. And maybe G2 is just one of such a one of these knots. And as James points out, this is good theory, because we must be able to see that particular star. And if we don't see it, if we essentially exclude all visible stars, the idea itself is excluded. So that's good theory in that sense. The future perspectives I want to mention is that 2016 offers a very unique observing possibility. Essentially, we can measure the position of G2 again and then see whether it follows the Keplerian orbit or not. In 2016, the difference between the drag force orbit and the Keplerian orbit is large enough that we can safely make a statement on that. And also we can see whether G2 extends to the level G1 was extended in that picture, as you've seen. So both observations probably would make it very hard for stellar models to survive if one of these observations were true. In general, of course, the G2 and G1 motion probe the accretion flow. So I think that's something nobody has actually used so far to know what is the conclusion for the accretion flow. And of course, gas at any time still might accrete onto such a star, and that would still be significant. I just remind you that, of course, we know that the black hole from time to time got more food. Here, these X-ray echo observations with XMM and Chandra, Mike Muno, Gabriele Ponti, Micah Clavel, and so on. And instead of having conclusions, I would like to say that this event of G2 is completely different to a tidal disruption event we have discussed so far. Yet, I think it's pretty fair to say this is a tidal disruption event. We can see the tidal evolution. That is unlike for the tidal disruption events discussed so far. We have not seen any radiative reaction. That's unlike. It's planetary mass only. It's not stellar mass. We only observe inside the tidal radius. And the pericenter distance is rather large. We picked it way before pericenter. That's also different. Pericenter lasts more than a year, simply because it got stretched so much. And we know that it's at the center of a galaxy. We really know that. The only similarity which comes to mind in some sense is that the black hole has a similar mass. 4 times 10 to the 6 is a typical mass we have discussed before. Thanks a lot for your attention. Yes, so I'm thinking of for example, a binary star where winds shock, and essentially you add 2 vectors and get an unlucky vector which points towards the black hole, some model like that.
Like the wind would collide like this.
Yeah.
The vectors there, the wind would collide like this.
Something like that, but I'm not a theorist. I can only draw arrows on a board. I don't know if that works out numerically. But there, of course, that tail has been going to an interesting direction, namely to the direction of IS-16 southwest, which we know is actually a compact. It's a contact binary of 2 windy stars. So, but as you've seen, that L-band streak goes further in radius. If that is connected, that is very unlikely. I think Gunther will comment on that in the following minutes. Well,
is any of them ruled out or by now?
Well, I think the NOVA idea is sort of the one which has been least followed up. I think all the others are hard to rule out. I think in the Murray-Clay paper there is the rate calculation is somewhat biased towards making it possible. So I think the rate and or the probability that we would see it is sort of overestimated by something. But all the and of course the windy star issues, they have the problems with the bracket gamma luminosity that doesn't match. So But I wouldn't be, I wouldn't a priori exclude models now.
Stefan, is there any model with a central star that is consistent with G1 existing on the same orbit, apart from chance?
I mean, apart from chance, I don't know anything. That's you have.
But if you have some kind of an envelope, and it goes, the global might be stopping each time, you might have some guys in the orbit.
So Hagai has more fantasy than I. I see James in the back there.
The min-max loss rate from IRS 16SW, is that enough to explain, say, 1 GQ for a decade?
I haven't checked that. Good point. Yeah, it's an easy rate estimate which one can do.
It is possible to resolve the gaseous component on the sky, but what about the cross-section of the component? Can you say what's the area of the cloud? What's the cross-section of the cloud along the Earth?
Not really. I think we have in our deepest observation, you can see it's barely resolved, but that means that it's essentially you have the PSF and you see that it's 5% too wide, the PSF, and that's it's very hard. It's simply at the limit of what the. But G1 was resolved nicely in 2004 in the CAC data. So if it behaves the same, we should actually be able to see in 2016 such an extent.